This lesson is about magnetic energy and inductance. We define the magnetic energy as the integral throughout space of the dot product between the B field and the H field, multiplied by 1/2, as you see in this formula. Since there is a proportionality relationship between B and H, we could also write this integral in terms of H only, in which we have the square magnitude of H. Of course, the quantity that we integrate can be called density of magnetic energy, which is simply 1/2 the dot product of B dot H. Now let's consider a system, a loop, in which a current I1 flows. This current I1 produces a field B1, and let's consider that this loop is the boundary of a surface S1. We plot here the surface and the normal to the surface. This normal is oriented in the direction that we obtain from the right-hand rule once we know the direction of the current flowing in the loop. So let's compute the flux through S1 of the field produced by I1, which is B1. We have a double index here because we compute the flux through S1 of the field produced by I1. If we divide this flux by the current itself, I1, we obtain a number, L11, which is the self-inductance of the inductance of this loop, which is independent of the current. It only depends on the geometry of the system. So the total expression for this inductance is mu/4π times the flux of the B field that we obtain from this wire, that we obtain by Biot-Savart law. So this is the expression that we obtain for the B field produced by this current, in which we have also divided by the current. So this expression doesn't depend on the current, only depends on the geometry. We also know, to recall, that there is a relationship between inductance and the energy, magnetic energy, that says that the magnetic energy could also be written as 1/2 the inductance that multiplies the square of the current flowing in the loop itself. Now let's consider a system of two loops. Let's call B1 the field produced by the single loop. Now, the current enters here, as you see in the picture. It rotates on this loop, and there is a second loop, go down, which is identical to the former and very close to the former. So the current rotates, and exits the system from this other wire. So the total B field produced by these two loops is twice the field produced by the single loop. And therefore, the flux through a single loop surface surrounded by the loop, is twice the flux produced by the single loop. But the total flux concatenated is the sum of two fluxes, that through loop number 1 and that through loop number 2. So that we have another factor of 2, and we can say that the inductance of this two-loop system is 4 times the inductance of the single loop. Now, let's consider a system of n loops on which a current I flows. Current flows, and exits from the other wire. What we know is that say that we have n loops, and from the previous expression, since the field is the sum of the different fields, and therefore the flux through a single loop is the sum of the different fluxes, the flux through the whole of the loops, through the n loops, is related to the flux of the single loop by a factor n squared. And the inductance related to the inductance of the single loop is n squared. Now, what we know is that B, we are computing the flux of B is related to H by proportionality, in which we have the absolute permeability, vacuum times relative. Therefore, if we substitute inside this multi-loop system a material which has a high value of permeability, what we obtain is a great increase of the inductance. So this is a way to realize inductors using some ferromagnetic material surrounded by wires that go on which a current flows. Let's make now this simple computation. Let's suppose that we are in the presence of this material, ferromagnetic material, which is orange here. This cylinder has an area A here and has a length L. A current enters here, goes around, around, around on these n loops and exits from the other wire. So we want to compute from Ampere's law the value of magnetic field, of induction, and also of inductance. What we know is that we have Ampere's law, so the total circulation of H through this blue contour must equal to the total current flowing inside. The total current is n times the current entering this system. And what is the circulation of H? We have a strong H here inside and a very weak H outside. So we can neglect the field outside in favor of the field inside, and we can consider that the field inside is constant by some symmetry considerations. So we have that the circulation of H can be approximated quite roughly as the product of the value of H times the length of this solenoid. And B is simply mu, it is note mu r, times the magnetic field obtained from this expression, which is simply Ni divided by L. So what is the flux of this B? Through a single loop is simply B times A. Through the whole of the loops, the whole concatenated flux is n times the previous one. So we have that the total flux obtained, a concatenated flux through this solenoid, is simply the flux of B, which is B times A, but one for each loop, because it's the complete concatenated flux of the system. After substituting and divided by I, the current that enters in the system, we have the expression of the inductance, which is mu naught mu r, so the absolute permeability, times the square of the number of loops, of turns of this wire, times the area, that is shown here, of the cylinder, divided by the length of the cylinder itself. There is another important parameter that we also studied in circuit, which is the resistance. So let's see a definition of resistance that is more related to the fields and to what happens physically. So let's imagine that we have a material, a section of material of conductivity which is not null, and we apply a voltage difference by 2 electrodes, as you see here. We know that inside the material there is a relationship, Ohm's law, between current density and electric field. So upon application of a voltage difference between these 2 electrodes, we have an electric field here inside, and therefore a current distribution. So we have V produces E produces J, which is proportional to E by the conductivity. Now, we know that J is a solenoidal field, so the total flux of J through a closed surface must be 0. And let's consider the closed surface as this one, green. It intersects our volume here with the surface S, and then closes outside by intersecting the wire on which the current I flows. The total flux of J is therefore this flux on S minus the current entering the system. Therefore, we can say that the current that enters the system here equals the total flux of J here. And this is the relationship between the current and the fields that appear inside the material. Another relationship that relates the voltage difference and the electric field is a well-known line integral from P1 to P2 with a minus sign of the electric field that gives the voltage difference. So our resistance of the system is the ratio between the voltage applied and the current that flows, in which the voltage applied can be written in terms of the electric field, and the current that flows can be written in terms of the current density that flows in the material. The current density is related to the electric field, so as you see, we have an expression of resistance which is strictly related to what physically happens inside the material, in which there are 2 integrals that only involve the electric field in the material itself.